How's it going, ladies and gentlemen? Mr. Johnny here again, looking at some 16.1 and 2 problems. So the objectives for these sections would be to be able to describe the Arrhenius definition of acids and bases, as well as describe acids and bases and their reactions in terms of proton transfer. So we're looking at a new definition for acids and bases here. We want to be able to identify acids, bases, and their conjugate bases acids, and describe what it means to be a strong or weak acid or base, as well as the corresponding strengths of their conjugate base acids. All right, so let's start with number one. It says, according to the Arrhenius definition, an acid is a substance that blanks. So what an Arrhenius definition says about acid is anything that increases the concentration of the H plus ion. All right, so things like HCl would be an acid because when they dissolve in water, they break apart to give you more H pluses as well as an anion. So anything that causes H plus to increase would be an acid. All right, Bronsted-Lowry base is a substance that accepts a proton. Now, the verbiage on this is a little different, right? So an acid for the Arrhenius definition gives off an H plus. Bronsted-Lowry base, we don't call it an H plus, but it's essentially the same thing, right? If we had an H hydrogen atom, we'd have one proton and one electron going around it. So what would an H plus be? Well, an H plus lost that electron, so now it's just literally one proton. So remember that an H plus is a proton. They're the same thing. So don't let that throw you off. Number three, which of the following is a Bronsted-Lowry acid? All right, so a Bronsted-Lowry acid gives off a proton, or it gives off an H plus, same thing. So let's see, this one would probably give off a proton. This right here, that's an organic acid group, so that's an acid. HF is an acid that we're familiar with, and HNO2 is also an acid. So it turns out all of those things are Bronsted-Lowry acids. Number four, what is the conjugate acid of NH3? So this is saying that NH3 is acting as a base. So if we start with NH3 and it's acting as a base, we're giving it a proton or an H plus. So what it becomes is NH4 plus. So that is the conjugate acid. Right? This is now able to act like an acid and give off an H plus if we're going back doing the reverse reaction. So we have a base here, and we have its conjugate acid on the other side. 5. What is the conjugate acid of CO3 minus 2? So again, this is acting as the base, and we want the conjugate acid. So that means we're starting with CO3 minus 2, and we're giving it a proton, an H plus. So now it's going to become HCO3 minus 1 instead of minus 2. So again, this was the base, and this becomes the conjugate acid. Again, if you looked at the reverse reaction, this would be giving off an H plus, which would make it an acid. 6, the conjugate base of HSO4 is, all right, well, if we're looking for the conjugate base, then the HSO4 must be the acid, which means it's giving off an H plus or a proton. So we would have something that looks like this. All right, well, if this was the acid, then this is the conjugate base. Because again, if you looked at the reverse reaction, it would be what's accepting the H plus. All right, and the conjugate acid of CH3NH2. All right, so again, this must be the base if we're looking for the conjugate acid. So we know that we're starting with that. And if it's a base, we're adding a proton to it. So we would get CH3NH3 plus. So this would be the base. I'm all about that base. No acid. All right, and that's it for that part. So I will see you guys in class.